Let's start talking about resting membrane potential. This is an important place to start when you're talking about how nerve signals work, which is our goal here. To understand resting membrane potential, we first have to make sure we understand what happens when more than one ion can cross a membrane. So let's set up a situation with the actual typical ion concentrations around a nerve cell. Now, I'm only going to show sodium and potassium. Chloride is also there, but chloride can't cross the membrane very easily in most cases, so it doesn't actually change membrane potential very much. We may bring it in later as it's necessary, but sodium and potassium are the two more important ones. So for sodium, concentration outside is about 145 typically. Concentration inside is about 15. Those are numbers you should know. For potassium, concentration outside is about 4, concentration inside is about 140. These are all in millimolar. Those are also numbers you should know. Now, we could use the Nernst equation to figure out exactly what ENA and EK are, but I'm just going to give you kind of our rule of thumb numbers. So if here's our voltage scale, here's 0. Before I do that, just test yourself really quickly. Take a look at ENA and tell me, is that going to be a positive or a negative voltage? Pause for a moment and answer that question. Okay. Positive sodium coming in. If I open the membrane to sodium, it will tend to diffuse in, which will make the inside more positive, and that is the voltage that will then push it back out. So ENA, the voltage I tend to move toward if sodium can cross the membrane, and the voltage which puts it into equilibrium, is positive. And in a previous lecture, we found that a 10 times concentration difference gave us an equilibrium potential of about 61 millivolts. This is just a little bit less than 10 times. And in this case, ENA comes out pretty close to about positive 60. So that's a number I want you to know. In a typical nerve cell that has these concentrations, ENA should be about positive 60 millivolts. Now remember, ENA depends on those numbers, so if I change those, ENA will be different. But in a typical nerve cell, you can assume those are the sodium concentrations, so you can assume ENA is about positive 60, which means that every time I open a sodium channel, I pull the membrane a little closer to that. Now, let's look at potassium. Pause for a moment and say, will EK be positive or negative? Okay, potassium's going outward. Positive ion going out makes the inside more negative. Now, will it be more than or less than 60? Take a look at this ratio. 140 divided by 4. What is that? I think that's about 35 times. So that's a bigger ratio than this. This is a little less than 10 times. That's about 35 times. So you'll need a bigger voltage to stop it. In other words, 10 times needs 60, 35 times needs something more than 60. So we expect this to be negative, more than 60. Nernst equation, actually, if you solve it, says that this is about, let's see, try to make this roughly proportional, move this a little bit down. This should be right around negative 90. So that's EK. So if I open a potassium channel, potassium will tend to move outward, making the inside negative. That actually tends to then pull the potassium back in, so we approach an equilibrium for potassium. Now, as we also mentioned in a previous lecture, let's just for the moment, this is not what it is in a typical neuron, but for an exercise, let's figure out what would happen if I had one channel for each. So each ion can cross the membrane about equally well. Again, that is not the normal case, but as an exercise, let's do it. So my one sodium channel means sodium comes in, which pulls me toward ENA. My one potassium channel means potassium goes out, which pulls me toward EK, making it more negative on the inside. They're both happening. I've got positive ions coming in and out, which means they're going to somewhat act against each other. But unlike in the example from the previous lecture with sodium and chloride, in this case they don't have equal tendencies to move. Potassium has a stronger concentration gradient. So right at first there will be more tendency for potassium to go out than sodium to go in. So if I've got a little more potassium going out than sodium coming in, what will happen to the membrane potential? Will it become more positive or more negative? What will the inside of the cell become? So if I've got more potassium going out than sodium going in, more positive charges leaving than coming in, the inside is becoming a little negative. So I expect membrane potential to move negative on this chart. How much? There actually is an equation you could use to solve that. It's called the Goldman equation, or the GHK equation. Feel free to look it up if you want. It's not actually that much more complicated than Nernst, but we don't actually need to do it. What we can say is that there's actually a couple ways you could do this. Here's probably the easiest one. We said that every channel pulls you toward that ion's equilibrium potential. Here I have one channel for each, so they're pulling equally. That means I should end up halfway between them. What's the average of positive 60 and negative 90? If I add those together, negative 90 plus positive 60 is negative 30. To make an average, divide by 2, and I get negative 15. A little negative. And that's actually where I would end up. But let's also think about why. Now remember, this is just an exercise. This is not a typical situation. But what happens at negative 15? Let's say that my membrane is a little bit negative. All right. I've got one channel for each ion, so each of them has the same number of places it could cross. Potassium has a stronger concentration gradient, meaning it has a stronger tendency to go out. So right at first, before this, potassium is going to leave a little more than sodium will enter, which is why I end up a little negative on the inside. Now think about what this does. Potassium tends to leave, but this tends to pull the positive potassium in. So it's tending to leave, but this is acting against it, slowing it down a little bit. Now think about sodium. This negative inside is attracting sodium inward, so both its diffusion and its electrical gradient are pointing in. So even though it has only one channel, it's getting pulled in a little more. So really, if I've got potassium has a stronger concentration gradient, but that's slowing it down a bit, sodium has a weaker concentration gradient, but that's speeding it up a bit, negative 15 millivolts is the place at which those balance out. In other words, I've slowed potassium down a little and sped sodium up a little, so now they're crossing equally and opposite. Which means once I hit negative 15, the membrane potential doesn't change anymore, because now I have equal amounts of positive charge leaving and positive charge entering. So this is steady state. It's not changing anymore. Except, is it at equilibrium? No. If I were in that situation, potassium is still leaving, sodium is still entering. These numbers will eventually start to change, and so this is not an equilibrium situation. It will eventually alter. But it is steady state. In other words, I have equal amounts of positive charge moving in either direction, so the overall distribution of charge isn't changing. I hope that makes a little sense. This is a challenging concept. This is difficult. So if this is a little muddy to you, or a lot muddy, do not feel like you're stupid. You're not. This is hard. You're going to need to look at this several times. You're probably going to need to try to answer questions, and you're going to need to ask questions and work through it. The best thing you can do to learn this is to look at this, think about it, and then come to me or someone else who knows this well, but I would recommend starting with me and saying, okay, give me a sample problem, and I'll set up a situation, and then you try to solve it live with me. We can do this on Zoom, whatever. You probably won't be able to do it at first, and that's normal. The important part is I can work through it with you and kind of see where you might be having problems and help resolve anything like that. Don't be embarrassed to do that. That's a necessary part of this. So that's how you're going to learn this. Now, let's keep going. Alrighty, so we said that's what happens if we have one channel for each. But that's not what a cell is actually like most of the time. In a nerve cell, a typical neuron at rest, we don't have one of each. In fact, I've got many more potassium channels than sodium channels. I'm not going to draw them in, but it's actually something like 40 times more potassium than sodium channels. So let's see what that's going to do. Each sodium channel pulls us a little toward ENA, each potassium channel pulls us toward EK. But I've got a lot more potassiums, so that's going to pull me much more strongly toward EK. Now if I did the math, what I'd find is that I'd end up somewhere around negative 70. Let's see if that makes sense using what we just talked about. What happens at -70? Think of this almost like a freeway. I've got one lane going this way and 40 lanes going that way. So which way is going to tend to get more traffic? Well, probably that one. It's a lot easier to move cars that way. So right at first, most of the traffic's moving out of the cell. That's why the inside gets more negative, all those positive ions leaving. But the more traffic comes out here, the more positive charge builds up out here, the slower the traffic can move in that direction. Whereas here, as all that traffic leaves the cell, here where the traffic wants to go in, there's more room. So it's easy now for positive ions to get in, for the sodium to get in, because now this inside is negatively charged. So the analogy we're using here is, here I've got a 40-lane freeway going that way. Here I've got a one-lane freeway going that way. But the more traffic goes out here, the more the traffic's going to jam up. So after a while, I've got a situation where traffic is moving outward through all those 40 lanes, but slowly. Traffic moving inward is moving really well on that one lane. So at some point, the number of cars leaving the area is equal to the number of cars entering the area. Slow traffic through a bunch of lanes versus fast traffic through one lane. Think about it with ions. Once the outside has gotten positive enough, potassium, which tends to go out, can only go out very slowly. We are close to EK. We're almost at the voltage where it wouldn't move at all. We're not quite there, so it is still moving out, but slowly. So each channel, we've just got potassium drifting out. Here, we're a long way from the voltage that would stop sodium. In fact, this negative inside, positive outside draws the sodium in. So sodium is coming in fast through that one. At -70, we're at the point where the outward movement of potassium equals the inward movement of sodium. So overall, membrane potential is no longer changing, and this becomes a steady state. In a cell at rest, with these ion concentrations and this channel distribution, that is resting membrane potential. In a typical nerve cell, it's about -70 millivolts. Close to, but not at, EK. That number depends on the proportions of ions for sodium and potassium, in other words, ENA and EK, and the relative number of channels for sodium and potassium. If you change those things, resting membrane potential will change. But that's the idea of resting membrane potential. So, I could ask you a question like, for example, if I added more sodium channels to this cell, what would it do to resting membrane potential? You might say, more sodium channels, let's see. That makes it easier for sodium to come in, so more sodium coming in makes the inside more positive, so that's going to bring it this way. It would make resting membrane potential more positive. That would be correct. You could also say, more sodium channels increases the pull of ENA, so that brings this up some. That would also be correct. Two different ways of thinking about it. A harder question would be to say, what if I increased this number? So I want you to think about that one. What would it do to resting membrane potential if I increased the concentration of potassium outside the cell? I want you to come up with an answer for that one on your own. Feel free to bring it to me during Zoom. But what you should be thinking about is, how will that affect EK? And thus, how will that affect resting membrane potential? Think about EK as being suspended between these two voltages. If I change one of those, EK still has to be between them. So think about what will happen to rest. Sorry, EK doesn't. Rest has to be between them. So if I change one of them, think about what that will do to rest. Okay. So that's kind of a quick overview of why resting membrane potential in a typical nerve cell is -70 and what goes into setting that. Now, the next thing we're going to be talking about is how cells change their membrane potential. So keep in mind, resting membrane potential is not equilibrium. We are not at equilibrium here. Sodium is still leaking in, potassium is still leaking out. In fact, we also need to talk about another thing here about that, because if I just let this sit that way, these numbers will eventually change. So how do I avoid that? If I'm sitting at rest, that's kind of like sitting in a boat that has a slow leak. The boat is going to be afloat for now, but eventually it's going to start to sink. So what do I do? You might say, well, plug the leak. Well, if I plug these channels, I have another problem. If I close up all these channels, yeah, that stops the leak, but then the cell can't do anything. What else could I do? Well, I could toss the water out of the boat, and as long as I keep doing that, I won't sink. That's more what the cell does. In order to deal with the fact that at rest, sodium is leaking in and potassium is leaking out slowly through all those channels and quickly through that one. Let's draw that by making this arrow much bigger. What could I do to counteract that? Well, we talked about membrane transporters. Nerve cells include in their membrane an active transporter, the sodium-potassium pump, also known as NAK-ATPase. We've mentioned this one before. This pump moves 3 sodium ions out of the cell in exchange for 2 potassium ions into the cell. So as my sodium is leaking in, this pump puts it back out. As my potassium is leaking out, this pump pulls it back in. So this pump is helping to counteract those ion leakages and make sure these numbers don't change. If you want, no, that's too silly of an analogy even for me. But by running this ATP using pump, we counteract those and keep those ion concentration gradients the way they are, which means my membrane potential can stay at this resting membrane potential. Those numbers don't change, so ENA and EK don't change, so rest doesn't change. We want this cell to be able to stay at a stable resting membrane potential. Why do we want that? Because changes in membrane potential are nerve signals. That's kind of how nerve cells work. So we need this to be our starting point so that when things change from that, it can be an important event. It can be something we notice. That's going to be how we send signals. So, in the next part of this lecture, we're going to talk about how sitting at resting membrane potential, we can cause changes, and those changes are a kind of signal that can travel from one place on the cell to another. The first kind of change we're going to talk about is a graded potential, and the second is something called an action potential. So, see you in a second. Let's talk about graded potentials, the first kind of nerve signal. So as we mentioned, this is a change in membrane potential that can spread from one place to another along a cell. Now, everything we've done so far with our cells has implied that a change that happens in one place affects the whole cell at once. But that's not actually the case, and let's see how that might work. So what I want you to imagine, if I had a nerve cell here, let's imagine that we're looking at a little bit of the dendrite, like this spot right here. So we'll draw this out like so. So I'm looking at just this last part of this dendrite right here. Now, I'm not going to draw them in, but keep in mind that we have all of those simple, what we sometimes call leak channels, the sodium and potassium channels that we mentioned when we talked about the resting membrane potential. We call them leak channels sometimes because they don't really open or close much of the time. They're just sort of there, and they allow that slow leak of sodium and potassium, which is actually where we get our resting membrane potential. So imagine all the leak channels are there, which means all of this cell is currently at resting membrane potential at -70. At -70, that means the inside is negative compared to the outside. So let's just sketch that in here. Outside positive, inside negative. And what I'm going to do is pretend that I'm monitoring the membrane potential at 3 different places. A, B, and C. Now, let's put those as if we were graphing them. Here's what's happening at location A, B, and C. And at each of them, here's resting membrane potential, -70. They're all going to be lined up in time, so we're monitoring all of these all together. Now also here, I'm going to imagine that I have a set of sodium channels here, but these are not leak channels. These are going to be some sort of gated channel. So right now, these are closed. And since they're closed, they don't affect the membrane potential. No ions are flowing through them. So right now, the membrane potential at all three locations, A, B, and C, is steady at rest, at -70 millivolts. Okay, hopefully everyone knows our situation here. We're just watching the membrane potential, and it's the same all along here. Now, at a particular time, which we'll mark on these three charts as here, we're going to release whatever chemical gates these. So whatever, this is the ligand for those channels. And just for a moment, we're going to go poof and put a little of it on there. Which means those channels are going to open. When those channels open, that adds to the amount of sodium that can cross the membrane at that point. And you can think of that in a couple of ways. You could think of that as the membrane potential getting pulled toward ENA, in other words, becoming more positive. Or you could think of that as allowing more sodium to go through those channels, which makes the inside more positive. Either way leads you to the same answer. So right here at location A, when I put that ligand on those channels and cause them to open, the membrane potential here at location A becomes more positive. So you see there the line going up. But what's happening here at location B and location C? At this point, nothing. Nothing's happening here. So while we have positive sodium ions coming in here at location A, and that's making the membrane potential here more positive, nothing has happened over here. So at these two locations, membrane potential remains at -70. Alrighty, so now what happens here? Keep in mind, this inside is not full of nothing. This has sodium and potassium and other ions sitting around in there. So when I let in these positive sodium ions, they are going to have an effect on other ions nearby. Primarily, if there are other positive ions around here, which there are, mostly potassium actually. Let's draw in some other positive ions here. How will they react to this sudden flood of positive charges? Well, positive charges repel positive charges. Like charges repel. So as these positive charges come in, they kind of shove the other positive ions out of the way. So what we can imagine is these positive ions getting pushed away, including here along this membrane. So at the next moment in time, this spot on the membrane has a little more positive charge getting pushed under it. So now this spot's a little more positive. And those positive ions shove other positive ions out of the way. And so on. What we have here is sort of a shock wave. You could imagine this. Imagine that we had a room full of people packed in fairly tightly and all just kind of bumping around and bumping into each other. And then we open a door over there and a whole bunch of people come in. Now, as they run into the first bunch of people, those people get shoved into the people next to them, who get shoved into the people next to them, who get shoved into these people. Each individual person is not moving very far. But if you looked from above, you'd see, as the door opened, sort of a shock wave. It was bump, 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 bump. People getting pushed away. That shock wave is what's spreading along this cell. And pretty soon, it will reach location B. Now, think about what's happening here at location A. We're going to assume that we close those channels. In fact, we can draw this as saying they're open from here to here. So this is where they open, and this is where they close. Once they close, the positive ions that we let in are going to just sort of dissipate. Some of them are actually leaking out through ion channels in the cell surface. To some degree, they just sort of settle into a new position, spread out again the way they were. So the effect, once I close these channels, is for these things to dissipate. So the change in membrane potential here at location A is going to dissipate. It's going to go back to resting membrane potential. Here at location B, though, after a little while, that wave gets to location B. Now, some of it has dissipated. Some of these positive charges getting shoved around have left the cell. There isn't as much left here. It kind of drops as it spreads. It decays. So the effect I see here at location B will be smaller. Notice location A was bigger, location B is a little smaller. And after a while, a little bit of the signal will get to location C. But by that point, it may be quite small indeed. So you can see that the signal took longer to get to location B and even longer to get to location C, and it was smaller by the time it got there. Think of this as if you were standing here, your friend was standing 100 feet away, and you had another friend 100 feet past that, and another friend 100 feet past that, and so on. And I make a noise. I go, "Hey!" My friend 100 feet away will hear that fairly well. They'll hear, "Hey!" And the friend beyond them will hear, "Hey!" And beyond them, "Hey!" And eventually they won't hear it anymore. It's a very similar phenomenon. When I make a sound, I cause a pressure wave in the air. Each molecule doesn't go that far, but it pushes on other molecules. But the effect gets smaller. There's effectively friction between the molecules. It dissipates in all directions, so some of that energy is going in other directions. All of that is very much like this. Or a ripple in a pond. I drop a rock in, and I make a ripple in the water that spreads out, but it doesn't spread forever. This is very similar. The change in membrane potential I caused spreads but decays as it spreads. This spreading change in membrane potential is a kind of nerve signal. We call this a graded potential. Graded potentials are one kind of nerve signal. It's a spreading wave of change in membrane potential that gets smaller as it spreads. So this spreads across the membrane, decays as it spreads, so it gets smaller. What else can we say about it? This one was depolarizing, positive, because I was letting in positive ions. But what if I'd been letting in negative ions? If I let in some sort of negative ion, like chloride, it would have made the inside more negative. So rather than an upward change, it would have been a downward change. But other than that, it would work exactly the same way. Those negative ions would push other negative ions, and I'd get a spreading wave of hyperpolarization. So graded potentials can be depolarizing or hyperpolarizing. We'll abbreviate that, dipole or hyperpole. In other words, they can be positive or negative. How big was it? That kind of depends on how many channels I opened. Had this been a lot of channels, it would have been a bigger change. So graded potentials can be of any size. They can be tiny, in which case they don't spread very far at all, or they could be big changes, in which case they'll spread farther. So these can be of any size. Again, kind of like a ripple in a pond. It can be a big ripple or a small ripple. Now, what else can we say about this? Well, what if, just imagine, I had at the same moment open channels here and here. The change from both would spread out, and when they got to B, the two changes would add together. So just like if I have a ripple coming one way and a ripple coming the other, the effect when they meet is the two of them added together. Graded potentials are the same way. They add when they meet. That's an important characteristic. So they can't spread forever, but when they meet, they add together. They could sum together. And that's, if I have a positive and a positive, they'll sum into a bigger positive. A negative and a negative, they'll become a bigger negative. A positive and a negative, they'll cancel each other out, partially or completely, depending on their size. So, if I cause a change in membrane potential at one spot, usually by opening or sometimes closing channels, what I'll get is a graded potential, a spreading wave of membrane potential change that spreads out from that spot. Now, that is a kind of nerve signal, but the problem is they don't spread very far. So in this, if I have a nerve cell like this, and I start a graded potential here, if that, say, is a nerve cell that extends over a few inches, that graded potential will probably spread no more than a millimeter or two. They don't get very far. So this graded potential will die out as it spreads, which kind of makes you wonder, well, what's the point? If your cell is anything but a very, very tiny cell, if that signal dies out, what good did it do me? And some of your nerve cells are quite long. The nerve cells that control the muscles in your feet have their cell bodies here in your lower spine. They can be a meter long or more, and in other animals they can be even bigger than that. So how can a signal spread over that far of a distance? We need some way of getting a signal that can spread over effectively any distance without dying out. Graded potentials alone can't do it. Now, if I wanted a ripple, if I wanted a sound, let's go with a sound. If I wanted to say, hey, and have that sound heard by someone in, say, Boston, I can't yell that loud. No matter how loud I yell, that sound will die out before it gets to Boston. I guess I could use a telephone, but that's cheating, right? How could I do it just with people? The only way I can immediately think of is that if I have a person every 100 feet or so, and their job is to repeat what they hear me say, then I can go, hey! And the person down there goes, hey! And the next person goes, hey! And so on. If I had enough people, that signal could spread, well, anywhere, as long as I have enough people to spread it there. So maybe, if I had some way of taking this graded potential and renewing it, saying this graded potential causes another graded potential, which causes another one, then that could spread over any distance as long as I could keep renewing it. Well, as it turns out, that is the idea behind an action potential, which is the next thing we're going to talk about.